It's going to be a little introductory video on solubility equilibrium. So you've had gas equilibrium, acid-base equilibrium, and now you've got solubility equilibrium, just means how much can dissolve. So when we do this, we're not dealing with compounds like this. We're not dealing with like sodium nitrate, okay, or potassium chloride, because those compounds are completely soluble. Obviously, there's a saturation point where you can't dissolve any more of those, but these are considered soluble. We're dealing with those compounds at the beginning of the year I told you were insoluble. Okay, they're actually not completely insoluble. They're always just a little bit soluble. So for example, a lot of compounds with silver, lead, mercury, remember, are insoluble. So let's say we have a compound such as lead chloride. So we put some of that in water. So here's some lead chloride in water in a beaker. Okay, that may be hard to see, but if you look at that, there is some lead chloride on the bottom. There is some dissolved. Okay? So this solution is saturated. We have the maximum amount that can dissolve at this temperature. So if we write the equilibrium here, so whenever something is slightly soluble, okay, if it was like sodium nitrate, something with nitrate in it, we pretty much draw a one-sided arrow and say, okay, this as a solid, put in water, and it makes aqueous sodium ions, aqueous nitrate ions, pretty much one-sided. Now there is a certain amount where we can't dissolve anymore. This, that's considered an insoluble compound, we're going to say is in equilibrium, and it produces lead ions. Again, these would be aqueous. That is some solid we put in water. So we're putting it in water. Some of it dissolves into lead ions plus 2 moles of chlorine ions. So really important to understand that these things are aqueous. This is the solid. So again, this is temperature dependent. Most things, as you increase temperature of the water, will move in this direction. You can dissolve more of them. Not everything is like that, but a majority of things that are solids like that. So if we write the K expression here, in this case it's called the KSP expression. It's called the solubility product constant. So we had Ka for acids, Kb for bases, Kp, Kc, so we had all those things. This is K for solubility. Same thing, we always do products over reactants, but in this case our reactants will always be solids. So for acids, we had an acid like HF going to H plus F negative. This was soluble, this was aqueous, even though not all of it split apart into ions, it was still aqueous. That was aqueous, that was aqueous, so it was always these concentrations over this concentration. In this case, since it's a solid, it's just going to be those two things. The only things that are aqueous and gas are part of the K expression. So we're going to say KSP equals the concentration of lead ions, again, that's in molarity, to the first power, because there's no coefficient, times the concentration of chloride ions squared. So again, there is a maximum solubility that these can be at a certain temperature. The KSP value for lead chloride is 1.7 times 10 to the negative fifth. The smaller this number, that means there are less things dissolved, meaning it is less soluble. Okay, so we can kind of look at KSP values and go, okay, if it's got a really, really, really small KSP value, say it's that times 10 to the negative 30th power, that means that there is not very much of this stuff. It's staying pretty much as a solid. Not dissolving very much. The bigger this number is, in this case, this is a fairly big KSP, the bigger this number is, that means that these things multiplied together give that. Okay? Solubility product constant. Solubility product, it's the solubility of that and that, it's their products equal this. So the bigger this number is, that's the bigger those were, it means the more it was dissolved. Again, it will always be the maximum amount. So I happen to know for this compound, the solubility of it is 0.00162 molar. That's the maximum amount this can dissolve. That means that this concentration is 0.00162 molar. That means this concentration would be that times 2. because there's twice as many of these. So this one is 0.00324. Sorry, I have that wrong. It's just 1 0. So the concentration of lead ions is 0.016 molar. Concentration of chloride ions is 0.032 molar. It's twice as concentrated of those as those. If you would multiply those together, so you put that in there to the first power, that in there to the second power, you get this. You cannot get a number bigger than this. That is the maximum amount of these that can be dissolved. You cannot dissolve any more than that. So if we try to dissolve 0.1 molar of this and 0.2 molar of that, you're not going to dissolve all that because that's going to give you a number bigger than this. So we can only dissolve a maximum of whatever this equals to when you multiply those. That is just a little intro to what KSP means. Real quick here, kind of the way we'll use this would be this. And we'll say, let's say we have some lead nitrate, which is soluble. Okay, it's got nitrate in it, so it completely dissolves. And let's say we have some potassium chloride, which is completely soluble also. So there would be no KSP values for these. It would be very large KSP values if there were, because these completely dissociate, and dissolve. But if we mix those two solutions together, put them in a beaker, now we're going to have some lead ions, some nitrate ions, some potassium ions, and some chloride ions. And anything with potassium, anything with nitrate stays aqueous. But lead and chlorine, some of them will dissolve, but some of them will form a precipitate as well. Okay, so if this was like 0.1 molar and this is 0.1 molar, we're going to have enough of these to be bigger than the KSP value. So some will dissolve, but a majority of them are going to form some solid lead chloride on the bottom. Again, potassium and nitrate would be spectator ions, would stay dissolved in the solution. That's all for this.